Hi, I'm Dr. Matthew Michael. Here I teach at New Jersey Institute of Technology. I'm going to continue on my series about Calc 3, and this time we're going to talk about vectors. Specifically, we're going to take a look from Larson and Thomas's textbooks on vectors. So in Thomas, that will be section 12.2. So there are a lot of different ideas when we talk about vectors, but we're going to be specifically talking about things that we can talk about from the physical aspect. We're going to be talking about things that have magnitude and direction, like velocity, force, acceleration, torque. Torque will also show up again later, and angular momentum. These are the things that frequently will go from one place to another. And so we're going to be talking about how it affects space, how it affects calculus, how it affects curves. We're not so much going to talk about the spaces themselves of the vectors, like vector spaces and algebras and like that you see in linear algebra. I'll let that stay there. We will take some of the consequences of that. We will take some of the stuff from it, but we won't spend a lot of time talking about linear combinations, determinants. Well, determinants will pop up. Like I said, we'll take little bits and pieces, but we won't really get into the theory behind what's going on. We'll just use some of the byproducts. In its essence, a vector goes from one point to another point. This is one version of it, in that if it goes from point A to point B, a vector in between these 2 points would be called AB. Notice it's going from point A to B, so that's a direction, and it has a length that we already know, and we can calculate using the distance formula. And it doesn't matter if it's in 2, 3, 223 dimensions, vectors will still work. It'll still, different things, show the same basic thing, that at this point the curve is traveling at this velocity in this direction. Sound very, very familiar? This is basically the derivative. And so that's why we see v for velocity. But I do want you to note that these vectors are going to be describing magnitude and direction. And on this curve, there might be multiple places where it has a velocity like this. And it will be the same vector. It won't be v1 and v2. It will be the same thing because vectors don't have homes. They're homeless. Instead, they have defined qualities of length and direction. This is different than points. So points exist at a specific point but have no other quality. They stay at home. Vectors are adventurers traveling into the unknown, going wherever, whenever, but they're always going in the same direction, exploring that one direction. So we also frequently need to have a way to write this new thing, because we already have a notation for writing points. So if we're in 3 dimensions and it goes from the origin to the point v1, v2, v3, the parentheses say this is a point. I need a different notation. So I'm going to have hard angles. Notice there's a different symbol to differentiate between points and vectors. Also, I want you to note that there are different ways to represent vectors. Earlier I mentioned the arrow notation, and so when you write it out, frequently people use the arrow notation. More commonly, if you just have a single letter for a vector, like v, that we will be using, it will be in bold. Just notation, but arrow or bold font mean the same thing. As I mentioned, this is to differentiate between the points. So, how do we find the distance? Well, remember v was defined as, since v has no home, why not just start at the 0 point and it ends at some point v1, v2, v3. And what is the distance 0, 0, 0 to v1, v2, v3? But the distance formula. Square root of v1 squared plus v2 squared plus v3 squared. This has multiple names: magnitude, length. This is also what's known as the norm of the vector, but we'll mostly call it magnitude of length. You can add vectors together just by adding components together. Make sure they have the same number of components, because it doesn't make sense to add a two-dimensional vector to a three-dimensional vector. Also remember that we have if scalar multiplication, if I take the same vector and apply it multiple times, it's the same thing as going in the x direction, k times, going in the y direction, k times, going in the z direction, k times. So k times u is just k u1, k u2, k u3. Here's a representation of what it looks like to have vector addition. Notice in part B over here, this is the parallelogram law of vector addition. Frequently when we build this u plus v vector, though, we'll use the part A part. It's right here. But however you like to build it, works for me. So blue arrows are original vector u. Notice these are just different components. Notice if I make a negative component out in front, so -2, -1, it flips directions of the vector. Makes sense. If I was originally going 1 unit to the right, 2 units to the top, 2 units up, and I made it negative, that means instead of going 1 unit to the right, I'm going to go 1 unit to the left, or opposite direction, since your camera will be opposite for you. If it's 2u, that means I'm going to go twice as long. It's 1.5. I'm going to go 1.5 times as long. Remember, when we're subtracting matrices, we're just adding the inverse matrix. So if I have u and v, I'm going from here to here. That means I'm here. Instead of going this connection right here, you can see this right here. V wants to go up. So it's the same thing as u, and then in a negative direction, v. And remember, this also builds from the parallelogram law. So this is the same length as this, which is why they draw it like this. All the properties of vector addition. Nothing should be too mind-boggling here. If you're adding vectors, it doesn't matter the order. You can group them however you want. Adding 0 to a vector doesn't change anything. Multiplying by 0 gives you 0. Multiplying by 1 gives you the same thing. These are the basic rules. Notice there's not a lot of multiplication unless it's scalar multiplication. So like 2 times u, 3 times u, a times b times u. These are all scalars. These are just constant numbers, not multi-dimensions. We're going to get into that in the next 2 sections. So if I have these two vectors, -1, 3, 1, and 4, 7, 0, and I want to find 2u plus 3v, we'll multiply both of these by 2 and 3, add their components, and it simplifies up to 10, 27, 2. Suppose you want to subtract them. Easy enough. Subtract their components. -1 minus 4 is -5. 3 minus 7, -4. 1 minus 0 is 1. Suppose, remember, magnitude is those two absolute values. Well, the absolute value. Sometimes you might see 2 absolute values on either side. In this case, it's going to mean the same thing. 1/2 u, that means, what is the length of half u? Well, move the 1/2 in, put it into the formula. So that's end up moving out a 1/2 out of the fraction. Notice there's the 1/2, it's hanging out by itself. So we see that the magnitude of 1/2 u is 1/2 square root of 11. So probably magnitude of u is the square root of 11. To make things easier, since we don't like doing the hard angles, although perfectly works for some people prefer to use unit vectors, saying that we've already done this before. We already have it in these notations of, in the point notation. We're used to thinking about things in terms of the x-axis, the y-axis, and the z-axis. So why don't we make vectors in those directions? So I is in the x direction, j is in the y direction, k is in the z direction. So any vector, here's linear combination sneaking in from linear algebra, any vector v can be written as a combination of these vectors. So if I'm going v1 in the direction of x, that's just v1i. I'm going v2 in the direction of y, it's v2j. So v is just, which is v1, v2, v3, is the same thing as v1i plus v2j plus v3k. And don't believe me? Take a look below. You'll see what I mean. Another cool thing is we like these unit vectors that we just talked about. Why not make every vector a unit vector? So we divide out by its magnitude, as long as it isn't the zero vector, because remember, we don't like dividing by zero. We can instead transform these vectors to the direction and its magnitude. And this gives us a bit of information that's interesting. We can say, why yes, this is how far the crow is going to have to fly, and this is the angle that the crow is flying in. So if I have the vector 3i minus 4j, remember that's 3 in the x direction, 4 in the y direction, 1, 2, 3, 1, 2, 3, 4. We can represent this as the product of its speed and direction of motion. Well, the magnitude is 5. So this reminds me of 3, 4, 5 right triangles. Divide the vector by its magnitude, you get 3/5 I minus 4/5 j, or the vector is 5 times the unit vector, 3/5 I minus 4/5 j. We also have midpoint rules that we can make vectors like this, going from 0 to the midpoint. This is just the same midpoint that you've seen before, calculated before in other classes. That's vectors. Hope this is helpful. If you have any questions, please let me know.